Hi everyone. Today I want to talk about the uses of lead, and this should hopefully give you a good bit of information to do the assignment today, which will be to pick one of those uses of lead and give us all some more details. So just a quick review. I've put some photographs up here of the way in which lead has been used in the past. Certainly things like lead sheeting, lead wire, lead pipe, bullets, colorings made with lead, lead weights for scuba divers. Lead's used in batteries extensively, and certainly lead was used in gasoline. And a lot of these colors were used in paint. And we'll go and dig deeper into each one of these uses. So I just want to start with this graph, which is one of my favorites when I teach about lead. And it's a graph that actually a friend of mine who works in lead put together. And it's the usage of lead on the vertical axis, and that's in tons times 1,000. Think how much lead that is, tons times 1,000. So here in 1910, 120,000 tons of lead was used. Axis here goes in decades from 1910 to 1990, when most of the lead use in the United States actually had stopped. And what you'll see is that lead was used a lot in paint in the early part of the 1900s, and then the use in paint started to fall through World War II. And after World War II, the use of lead in paint really diminished, so that by the time I was born in the early 1960s, very little lead was used in paint. The blue line here is the use of lead in gasoline, and until about 1930, very little lead was used. But then the car became something of a middle-class phenomena in this country. And people started to travel a lot more, and the use of lead in gasoline skyrocketed, and it peaked in the 1970s, which is pretty amazing to think about given how much we knew by then about the hazards of lead in the environment. And then government regulations began in the mid-70s, and the use of lead in gasoline plummeted, but it didn't end until the 1990s. The black dots here are the total amount of lead released here in the United States. And so at the peak, we were releasing 240,000 tons, 250,000 tons of lead into the environment. And that's really the context in which I'll build the rest of today. But remember that paint and gasoline are really the big ones for environmental releases of lead. All right, where's all this lead come from? How's it refined, and what's its most common use? So lead is primarily found in the mineral galena. Galena is pictured there. It's under me right now, so I can move me out of the way here. And it's a gray to silvery mineral. It's very dense, so it's quite heavy when you have a piece of it in your hand. It has what's called a cubic structure like this. So you can see it breaks into cubes. Here, that the lead crystal breaks, the galena crystal breaks into cubes like this. And again, it's made up of atoms of lead and atoms of sulfur in here. So it's a combination of lead and sulfur in this arrangement. Lead is also mixed with ores of copper and zinc and silver. In order to purify the lead, it's usually heated or smelted. We'll talk a little bit about that on the next slide. And about half the use of lead today is for batteries. So I put this map of the world up because it shows lead and lead zinc deposits around the world. And you'll see that those lead deposits are scattered all over the United States, from Alaska through Canada, the western U.S., the central U.S., even the east coast here, in Greenland, through the Arctic, Canadian Arctic, a lot in Europe, we're going to come back to that, through Asia, Australia. In Africa, most of the lead deposits are in southern Africa and far northern Africa, and then in South America, there are lead deposits. So lead's really spread around the world and has been mined, and it's been used around the world. All right, lead smelting. So how do you get lead out of these minerals? And remember, the minerals are geologic. They're naturally formed. They are concentrated in lead-bearing deposits for sure, but there are small amounts of lead in almost all rocks around the world. Getting lead out of the mineral galena turns out to be really, really easy. It's as simple as building a fire, putting the galena in there with the fire, and then pulling the lead out from the ashes. So when you're doing that heating, remember lead melts at only a couple hundred degrees Celsius. You release a corrosive sulfur gas, and you also release lead in the forms of small particulate matter. That's released to the atmosphere. So here are a bunch of British geographers that kind of look like British geographers out on a hike through the woods to look at old lead smelters in England, right here. And this is a stone lead smelter in England here. And here's a 16th century etching of smelting going on again in Europe here. And this is slightly more advanced. The smelter is built here out of brick. It's kind of a kiln. They can put the wood in here on the side. It looks like maybe the lead is pouring out over here like this. And they're making some lead pipes with what they've taken out of the smelter here. So long history. Lead was first probably smelted by the Turks many thousands of years ago in present-day Turkey. But every civilization, pretty much every civilization, has found lead and has used it as an easy-to-work metal. So what are some of the properties of lead that make it so useful? Chemical and physical properties. First thing is it's relatively easy to mine. There are surface or near-surface deposits exposed. It's relatively easy to refine because it has a low melting point. It's ductile, which means it's easy to deform or twist or bend. And it's easy then to work and to make objects out of. And this is again because it has a low melting point. Lead is very dense. We talked about that yesterday. So it's a great shield from radiation. It's also useful for projectiles like bullets. And it's dense because it has a very high atomic mass. It's big, quite large nuclei with a lot of neutrons and protons. So it's a dense material. Turns out that lead is rather resistant to corrosion. It tends to form a coating of oxides both in water and air. So an oxide is when oxygen chemically reacts with the lead, and once that skin of corrosion is formed around the lead, it doesn't react much anymore. So it can actually be used for things like storing very strong acids because there's a layer of corrosion right on the surface that protects the rest of the lead. Turns out in the early 1900s, somebody figured out that if you put a little bit of lead in fuel like gasoline, it'll help that fuel burn more smoothly. In other words, the flame front moving through the gasoline in a cylinder of an airplane or automobile engine won't explode, but will burn smoothly. And so lead was added to gasolines to help make engine runs more smoothly. It was added as an organic compound, and I'll show you that compound later, so that it could be dissolved in the gasoline. Turns out that lead oxide is very toxic. Lead metal is less so. And so lead oxide stops things like fungal growth or mold growth. And therefore it's really useful as a pesticide. It also kills insects. It's also useful for painting on the bottoms of things like boats, where marine organisms might decide to attach to the boat. It's toxic to those organisms, and that protects your boat. It's not quite so good for the marine ecosystems. So the fact that lead is toxic was actually one of the reasons it was used by people. And finally, in terms of painting, the lead oxide does something called chalking. And chalking is something that typically we would not want our paints to do. It's that they basically bleed off the outside of your house over the course of years as rain and wind hit the house. But the paint manufacturers thought this was an awesome idea because it meant you didn't have to scrape the paint off your house. It would simply melt off your house, and when it was done, you could repaint again. So that chalking process was put forth by advertisers as a great thing. It turns out not to be such a great thing because where does all that lead go? It goes into the soil right around your house. So let's look at some of the properties that make lead dangerous. Again, I'm going to be spending a whole lecture on lead and health, but I just wanted to put that forward right now. And the first thing is that lead exchanges with calcium in your body and in chemical reactions. They're very similar chemically. And that's not very good because there's a lot of calcium in your body involved in nerve signaling and building bones and those sorts of things. Lead is a neurotoxin, and by that I mean it attacks the nervous system. And it penetrates the blood-brain barrier, which is a barrier around your brain that prevents most things from getting in, but lead can get in there. And this picture here on the right showing imagery of a person who has actually ingested a lot of lead in the parts of the brain that are affected. So there's really good medical evidence now showing what actually happens to people's brains when they've ingested lead. And I'll go through some interesting and controversial studies that imply that when people's brains are affected by lead, it actually affects their behavior. And we'll do that when we get to the health portion. And I think what's really important now that makes lead dangerous is it's ubiquitous in much of our built environment because so much of it has been used in that environment. It's in pipes, it's in paint, it's in soils because of the use with automobiles. So it's a ubiquitous environmental contaminant that any place you go in this country, you're likely to find some lead that's not naturally occurring. All right, let's look at the first uses of lead. We're going to go back into the Roman times. And I pulled pictures of Roman coins made of lead. I showed you that last time. Easy to make the coins, easy to stamp them out because the lead was so soft. Down the bottom here, you'll see another one of those lead pipes. The Romans were the first ones who started with lead pipes like this. There's a Latin inscription on here. But some things I didn't know until I talked to Nico and started to work on this lecture is that lead was also used for makeup. So red lead was used for blush in the Roman times, and that's 3 atoms of lead and 4 atoms of oxygen here. And white lead, which is lead carbonate, so it's 2 atoms of lead and then this carbonate, which is carbon and oxygen, with lead associated with some water here too, the OH. That white lead was used for skin whitening by the Romans. There was also a dark lead compound used above women's eyes for Roman makeup on here, so that the Romans used a lot of lead in their coins, in their pipes, in their makeup, but they also used it as a sweetener in their wine, partially intentionally and partially because of the way they processed their grapes. And so one of the questions that historians have asked is, did the Roman Empire really fall from lead poisoning? And the hypothesis there is something called lead acetate was added to foods. And it turns out that lead acetate is really sweet. Sugar in those days was scarce. Natural sweeteners were scarce. And the lead acetate was a byproduct of making wine in lead vessels, especially heated wine and wine that had soured or gone to vinegar. And lead acetate chemically looks like this. So here's a lead atom. Here's some oxygen atoms. And here are some organic groups. That's a carbon and 3 hydrogen. So this is the lead acetate molecule here. And so it's an organic molecule carrying a metal in here. And that's a way to get lead into the human body. The fact that it tasted sweet led some people to speculate that lead was actually the first artificial sweetener. And the Romans were the first to use it. So here from Pompeii is a fresco showing Romans having a party and drinking wine that presumably was sweetened in part by what's called the sugar of lead, or lead acetate. So difficult hypothesis to prove here, but an interesting thought that perhaps the Romans were doomed by their use of lead. So Romans were busy melting lead, mining lead, and releasing it into the environment. And an amazing thing we can do today is we can actually, using really sophisticated chemical analyses, sensitive chemical analyses, we can track that lead over time. And the first work was actually in something called ambitrophic bogs. And ambitrophic bogs is a pretty picky name that might be useful to you one day in a Scrabble game, but not much else. But these are really cool bogs. Here's a picture of one. It looks pretty featureless, right? It's just flat, old dead vegetation and moss and leaves and twigs. The cool thing about these ambitrophic bogs is most of what gets into them does not run over the ground surface, but it falls out of the sky. And here's one of those schematic diagrams of how you might make one of these bogs. You've got a river channel, and then you've got a little area where the river's not flowing over, and a lot of organic material. And that organic material builds up over time, makes a slight mounding on which only the rain falls. And that rainfall puddles, and material falls out of the air with the rain and accumulates slowly in there. Scientists in Belgium went to one of these bogs, a couple 100 miles across Europe from where most of the Roman smelting was going on. And they took cores, so they stuck a metal pipe down through the bog, meters of material. They brought that out, they brought it back to their lab, they chopped it up into little pieces, and then they measured using an instrument called an ICP-MS. We're going to show you in a couple days an ICP-OES. But an ICP-MS actually measures the mass of each particle going through it, whereas our ICP measures the optical emission, the light coming from there. But with our ICP-MS, they could measure the amount of lead in each part of this core going back through time. And they took 2 different cores. The lower core here, they only had very rough resolution, I don't know, maybe 50 samples, 40 samples in here. This is the age. You can radiocarbon date the peat. And this is the time of the Romans here. So we could say this is 0 CE, the beginning of the Common Era. They've used the old-fashioned nomenclature here of BC and AD. So here at 0, sort of the peak of the Roman Empire. And what you can see is the lead concentrations are low, and about 300 BCE they start to rise. They really start to rise about 50 BCE. The yellow is the height of the Roman Empire, and then they crash. And by sort of 300 CE, they're quite low. This is a much more detailed evaluation from a second core where the samples were much smaller increments. It's exactly the same pattern. The rise starts here at sort of 50, peaks out at about 100, and then falls. So these bogs and the lead in them are tracing the Roman Empire and how successful it is and how much mining it's doing and how much lead smelting it's doing. But if you thought that's cool, to me this is even cooler. And maybe it's because I've worked in Greenland and spent time up there. But this is the Grip drilling dome. This was run by the Danes. It was a European drilling project. It went down through 3,000 meters. 3,000 meters, that's several miles of ice to the bottom of the Greenland ice sheet. And as they went down, they collected drill core that looks like this. This is ice. It's about 5 inches wide. This is a layer here of volcanic ash that landed on the ice from a volcanic eruption. But most of the ice is completely clear. The ice is drilled in Greenland. It's brought back frozen, either to Denmark or the United States. One of the United States centers that works on this is in Denver. The other is at the Desert Research Institute in Reno, Nevada. And here's a scientist. This is a woman scientist here who is pulling apart in Nevada, strange place to have a lot of ice, one of these ice samples. And what she did with those ice samples is cut them up into very small pieces, very thin slivers. And you can see when you collect an ice core like this, it's a difficult endeavor, it takes years to do. Different people get different parts of the ice cores. So some people get part of the ice core for chemistry. Some parts they analyze gases. They look at the physical properties. They measure isotopes. They put some away for someone who might want it 30, 40 years from now. Anyway, what she did was cut the ice core up and make measurements of the lead in the Greenland ice core. And you all should be sitting there thinking, how is lead going to get all the way from Europe up to Greenland? And when you look, here are all the Roman lead and silver mines. So, in Spain and some in Italy, in Greece and up in England and France. And here's Greenland. It's not a quick trip. Yet, the lead from the Romans made it to Greenland and to the North Grip ice core site in northern Greenland here above the Arctic Circle. And here's their record that they produced. And if we go back in time, this is the Iron Age, about 1,000 before Common Era, BCE. And then this is the Middle Ages, sort of 800 CE. And here's the lead pollution record in black. So we start to see the lead climb in Greenland. It does a big thing here about 800 CE. That's when the Phoenicians expanded their society. And it levels out again. And then when the Romans really get started in here, pops back up again. It crashes when there's a crisis in the Roman Republic, and then Rome gets it back together again with the Pax Romana, and up comes the lead production, and then the empire kind of collapses, and so does the production of lead, and therefore the lead moving from the mines up to Greenland. And the lead production stays low until the Middle Ages, where people get it together again, and they start mining, and up goes the lead in the Greenland ice sheet. So ice, clear ice like this, has little bits of lead dust that were transported from the smelters 1,500, 2,000 miles away. And we have a record of the Romans from far away in ice. It strikes me as just really cool that we can see what they did with lead. All right, so let's have a look at this uses of lead before you all spend some time putting these together. You're going to pick one of these and put it together in your website. Probably the lead that is most in the news is the lead in pipes. And the place most in the news is Flint. And Flint, Michigan was dramatically affected by lead when their water supply changed, when they went from water that was non-corrosive to water that was very corrosive. Flint was an industrial city, had not seen a lot of investment in their infrastructure, and there were miles and miles and miles of lead pipe still in the ground. And when the water chemistry changed, it started to eat away at the insides of the pipe, and the people of Flint, Michigan were poisoned. And again, when we talk about health, I'll tell you more of this story. But these are some pictures of Flint pipes. You can see the corrosion on the inside, and that's the corrosion that ended up in the water that the people in Flint drank. The questions when approaching where the pipes are and where this contamination coming from is really well done in this one sketch by some architects that I found. That lead could be in water mains owned by the city. That could be in supply pipes that go from the water main on the street to your house, and it depends on where you live, how much this is owned by you and how much is owned by the city. Or it could be in these yellow pipes, which are inside your house. Those are owned by you. So you have to figure out where these pipes are and get them out of the system if you're going to deal with lead in water, in drinking water, and you have to treat the water correctly. So here in Burlington, we have a very aggressive program for treating water so that it's non-corrosive. In Flint, the problem was they did not on here. In terms of remediation, the trick is how are you going to get these pipes out? Who's going to do the work? How are you going to find them? And who's going to pay for it? Lead-acid batteries are a huge use of lead. And I'm going to bet that most of you have had experience with these. If you've ever driven an automobile, there are lead-acid batteries in an automobile. There are lead-acid batteries in some other things around your house. The GPS units we used to use for location ran on lead-acid batteries. Fewer and fewer. Lawnmowers sometimes have them. Lead-acid battery relies on a reaction between lead and lead oxide through sulfuric acid. And the sulfuric acid is in between these plates of lead. And you'll know there's always a negative and a positive terminal on these batteries. And as the lead oxide forms and degrades and lead sulfate forms and degrades, you release electrons. Or when you're charging, you put them back on and you change this chemical reaction. So it's a reversible chemical reaction in the battery. The take home from that is that every automobile in this country has lead sitting in it in the form of these lead acid batteries. Of course, those last a couple years, and then if they're not recycled, they end up out in the environment. There's lead in bullets and shot and fishing weights. And it's been surprisingly controversial to get the lead out of things like fishing weights and get the lead out of bullets and out of shots. If you look online, you're going to find all kinds of things like this one I put up here that says, "Stop the fishing tackle ban." It's not really a ban on fishing tackle. It's a ban on using lead in marine or lake environments, which tend to be fairly sensitive ecosystems. Same thing with the shot, except the shot is even more interesting because lead shot ends up in things that people end up eating. So if you take a bird down with lead shot and then you eat that bird, you're probably eating some of that lead unless you get every bit of shot out of it. Lead is often used, or was often used, in both glass and in pottery glazes. And so I pulled some quotes here as I was looking for photographs. These are actually dinnerware from Mexico in here, which for a long time had a lot of leaded glazes in it. That has changed lately. But here's the quote, that lead has long been used in ceramic ware, both in glazes and decorations. When used in a glaze, it gives a smooth, glass-like finish that allows bright colors and decorative patterns to show through. It's often associated with rich or intense colors. So one can imagine why people who make pottery would want to use this. The downside is that if you eat certain foods that are acidic, or if you heat foods in these leaded glazes, they will leach lead into your food. Similarly, lead was added to glass to make what's called crystal. And it can have up to 35% lead. And when it does, when you tap on that glass, it sounds differently. It looks differently. It sparkles. It's funny, when we got married 26 years ago, somebody gave us a big lead pitcher because they thought we would want that. The only thing we've ever used that lead pitcher for is putting flowers in. It's really pretty for flowers, but we won't drink anything out of it. It's a leaded glass pitcher. Lead is used as a radiation shield because it's so dense. And I put two pictures here. The one on this side is laboratory radiation shielding. In the lab I got my doctorate in, we used a lot of this around places where we were trying to count radiation, and we wanted to stop any environmental radiation from getting in. But this lead shielding, these are lead bricks, could be used if you had a radioactive source and you wanted to protect yourself from it. Or I'm going to presume that you all have seen something like this when you've gone to the dentist, or maybe you have broken a bone and been x-rayed, and the technician has been wearing a gown like this, and that gown is made of thin lead and protects that woman or man who's giving you that x-ray from getting exposures to those x-rays that are being used to image your body. And it's particularly important that these cover sensitive parts of the human body, which is mostly the human reproductive tract, and also the thyroid in your neck. So you'll often see both of those covered by leaded garments like this. Lead was used as a pesticide. And in fact, in Vermont, lead was used very heavily as a pesticide because it was used for apples. So I found this old postcard of these men here spraying lead arsenate pesticide on apple trees. And you'll see that none of them are following their personal protective gear recommendations. Nobody's wearing a mask. This guy's sitting on the tractor just having a fine day out there while the spray is all around him. This was that arsenate of lead, and if you're a chemist or have had some chemistry, you'll recognize that arsenic is also a poison. So this was a double poison, arsenate and lead. Really good at killing fungus, really good at killing some insects. And this is a quote, again, that I pulled while I was reading about this. I couldn't write it any better, so I put it in quotations and cited it here. At one point, lead arsenate was the most popular pesticide in the nation, and that's around the turn of the century. The USDA, our government organization, recommended it broadly, and millions of acres were sprayed with it across the country to protect crops. As farmers increased the frequency of application, concern increased. Apples had to be soaked in acid to remove the residue off them. So you got to wonder what we were doing in those days. In fact, we often see some arsenic when we make analyses from samples in parts of Burlington, actually parts near where I live, which in the past were apple orchards in the mid-1800s. If you look at the old maps, areas just north of where our house is were apple orchards. And it's quite possible that some of the lead and some of the arsenic we measure in the soils here is from those lead arsenate pesticides. It doesn't degrade. They're elements. They're still going to be in the soil. The only thing that will happen over time is they'll get mixed and diluted. All right, so I want to finish up with lead in gasoline and lead in paint. So lead in gasoline, as I mentioned before, was an organic compound, so it would dissolve in gas. That organic compound is something called tetra. That means 4. Ethyl, this is the ethyl group, a carbon and 3 hydrogens, lead. And here's that lead atom sitting in the center with 4 ethyl groups attached to it. Tetraethyl lead. There's your organic chemistry for the day. What this meant is that tetraethyl lead could dissolve in gasoline. And that was used to reduce knocking. It was used as a lubricant in the upper parts of the cylinders. But the problem is when it started to be used in the 20s, people started getting sick, people in the industry. And in fact, the quote here is that at DuPont's manufacturing plant in New Jersey, 8 workers died from lead poisoning between 1923 and 1925. And if you went all the way back to the beginning of this lecture, remember, peak use in gasoline was actually in the 60s and the 70s. And yet people were dying 50 years before. So how would you know there was lead in your fuel? Well, you would look at your pump here and it would say, this contains lead. And we still buy unleaded gas today. You can't buy leaded gas for automobiles, but we still buy unleaded. And that differentiation I can remember when I was in high school, deciding whether I would buy leaded gas or unleaded gas for my car. And again, when we get to later in this class, I'm going to show you a whole series of advertisements for this, which I think you'll find really intriguing and pretty scary. A lot of the sales for lead reflected the way we dealt with other hazards, early sales for radiation, things like smoking, and now one of the ways in which we deny climate change. There's a real parallel there. But let me show you an advertisement right now. This is from YouTube, and it's an advertisement for leaded gasoline. And I think it'll give you some idea of why so many people use so much lead in their automobiles.
There, what does that look like? That's right, it's a pansy. But look how easily it can be made to resemble a chimpanzee. Yet there's a tremendous difference between the two. Just like there's a powerful difference between gasoline and ethyl gasoline. That's because ethyl gasoline is a high-octane gasoline. Gives more power on the road. Because the higher the octane number, the better the gasoline, the less likelihood of knock. You see, fuel knock is when the gasoline vapor in the cylinder, well, it just explodes. Now, this has about the same effect on the piston as, well, this fellow has on his piano by trying to move it with a kick. But with high-octane ethyl gasoline, there is no knock. The burning gases give the piston a smooth, powerful push. And that's the difference. And that's why ethyl gasoline brings out the full power and performance of your car. So next time you buy gasoline, drive up to the pump with the ethyl emblem and say, fill her up.
right, so something is missing in that advertisement, and it's the word lead. So they're using ethyl for lead, but they're not telling you that you're putting a toxic material in your car. There are all kinds of other things you can peel apart in that advertisement that we'll touch upon later. But this is the kind of thing that sold Americans and people around the world on leaded gasoline and killed probably tens of thousands of people and damaged many, many others. Okay, let's finish up here by looking at lead in paint. And again, the advertising for lead in paint was huge. So Dutch Boy was the company that sold, I think, the most of the lead paints on here and made the biggest fuss in terms of advertising. And I've just put some of these advertisements up here. Inside and out, white lead paint lasts, and it's supplied in many colors. So white lead was the lead oxide lead carbonate that's in the paint. But it could be tinted to other colors, and they show you pictures of all these bright colors, people painting, and these beautiful homes that you're supposed to envy on that. And lead paint lasts. So you should buy this paint because it'll last. They even made coloring books about lead paint with the lead family in it here. So lead in rubber on here, lead in toy soldiers. The Dutch Boy here with the paint and lead, telling you how good this would be. Color harmony in your home. And this one, is your house paint hungry? Many houses are. The wise homeowner sees to it that paint hunger is not allowed to become paint starvation. Look your home over today. If the paint is worn down evenly all over, more than likely it's Dutch Boy brand. This gets to the idea of chalking, where the lead paint simply melts off the house over years and then it's time to put it back on. But it's exactly that chalking that puts all the lead into soils that we now have to remediate. Okay, so that's our intro for today. Your assignments for today are here. We have a reading for you about the use of lead, and it's a pretty simple reading to go through and have a look at how it was used. And then we want you to take a deep dive into the history of lead use. We want you to pick one use of lead, and any one that I mentioned or any other one that you guys can find, totally fine. You don't have to pick anything particular, but pick one use of lead. And we want you to develop a new page in your portfolio about that use of lead. Tell your readers something about its history. Tell them about its environmental effects. You can extend that out to the effects on people and communities if you'd like. And then talk to your readers about the cost of remediation. This is going to take some work on your part, some digging and research on the web to figure out how much it might cost if you're going to remediate, say, lead in soil, or lead paint on a house, or dispose of lead shielding that you're using for an X-ray lab. So on your page, make sure to include 2 links to relevant websites, URLs for websites that we and others can go look at least 2 photographs, and then a 1-minute video of you describing this use of lead in an easy, accessible style for people to listen to. So that's your assignment for today. We look forward to seeing what you find out about lead, and we will see you all tomorrow.